OCR A, A-level physics. This is my third video on magnetic fields. So look at this animation. What am I doing? I'm holding a wire and I'm moving it into a magnetic field, and then I'm moving it out of the magnetic field, or rather I'm moving it through a magnetic field. And what's happening is that the wire moves through the magnetic field and an EMF, in other words a voltage, is induced across the wire while the wire is moving. In other words, while the wire is moving, one end of the wire becomes positive, the other end of the wire becomes negative. Yes? And this is called electromagnetic induction. Electricity, magnets are involved, and we are inducing, we are creating, we are making it happen, yes, an EMF, a voltage. Note that the size of the EMF depends on the speed of the relative movement. If I did it faster, I'd get a bigger voltage, and the direction of the EMF depends on the direction of the movement. Now, Michael Faraday suggested that we get an EMF when flux is being cut. So if you imagine between the poles of the magnet, if you imagine all of these flux lines which I've drawn in previous videos, and then what's happening is that the wire is slicing through these flux lines. Okay, it is cutting flux, and then the EMF is proportional to the rate of flux cutting. So the amount of flux which is cut every second. So Webers per second. Okay, and strictly speaking, that is Faraday's law, that the EMF is proportional to the rate of flux cutting. Now, Faraday's law, if you are asked OCR A, if you are asked in an exam, what is Faraday's law? You write down the induced EMF is proportional to the rate of change of flux linkage, because that's what OCR wants, okay? The rate of change of flux linkage. What's flux linkage? I'm going to talk about that in a slide or two. It's basically, you see the capital N there. Notice the minus sign. Don't worry about that. We'll come to that in a few slides as well, why that's there. Okay, and I'm not going to write dn phi dt. We're just going to write down delta n phi over delta t. So the change in flux linkage divided by time, or the amount of flux which is cut divided by time. Webers per second. Have a go at this question, and I shall show you the answer in 3, 2, 1. So there you go. So it's just basically the speed of the airplane times by its wingspan will tell you the area swept out, and then phi equals BA, so that's the amount of flux cut every second, and that from Faraday's law is equal to the EMF, 0.187 volts. Now, this is a coil with N turns, and looking at the diagram, we see that there's lots of flux going through the coil. Because there's lots and lots of turns, we don't just say flux now, we say flux linkage. So that's where this comes from. So N is the number of turns. So N phi is the flux linkage. Okay, and the flux linkage will depend on the flux density, and it will depend on the area of the coil, and it will also depend on the angle between the axis of the coil and the field. Okay, so looking at the bottom left diagram there, you should see that if theta is 0, then lots and lots of flux is going through the coil, and N phi will be BAN, or phi equals BA. And then if theta is 90 degrees, then there won't be any flux going through the coil, because cos of 90 is 0. Yes, so it depends on the flux density, it depends on the area of the coil, and it depends on the angle between the axis of the coil and the field. Yeah, the specification actually says phi equals BA cos theta. Now look at this. This is my coil, and now it's rotating in a magnetic field. And because it's rotating, the amount of flux that is going through the coil will vary sinusoidally. Yes? As the coil rotates, the flux linkage will vary like that. So that's n phi against time, and I've drawn it as a cosine. Now, from Faraday's law, we're going to get an EMF, and the EMF will also be sinusoidal. From Faraday's law, there will be an induced EMF in this coil, which will vary like this. Now, note that n phi we said was BAN cos omega t. Now, cos theta, because theta equals omega t, omega is theta over t, where omega is 2 pi f, which is the frequency of the rotation. You remember all the circular motion stuff we did, okay? So, dn phi dt, if we differentiate that, and we include this minus sign, we get BAN omega sine omega t. So we see that the EMF is actually a sine wave. So that was an AC generator. We are generating an AC voltage. And in these examples here, there is a turbine, and that turbine is making an AC generator go around. And in that AC generator, there is a coil which is rotating inside a magnetic field. It might actually be a magnet rotating inside some coils. It doesn't really matter. That would work as well. In fact, for the big ones, it's coils rotating inside electromagnets. But nevertheless, in the steam turbine, inside the wind generator attached to the blades, and there's a water turbine as well, they all have AC generators inside, rotating coils. Now look at this. This is something different now. Turning the crank. Look at this diagram. You're turning the crank, and it's a generator, and it's dead easy, really easy to turn the crank. Okay, there's a little bit of friction, but not very much. Dead easy to turn the crank. There's a bulb there, but the bulb isn't lit because we haven't got a circuit. Yeah, notice there's a break in the circuit. So what we do now is we close the switch, and the bulb lights up. So we're turning the generator, but there's a difference now. Turning the crank to make the generator work is a lot harder. We have to do a lot more work. Yes? We have to do a lot more work, and somehow the work that we are doing is being changed into the heat and light given off by the bulb. Okay, the energy needed to light the bulb comes from the work that you do turning the handle. And in both cases, you are inducing an EMF, but in the second case, you're actually inducing a current as well. And because you're inducing a current, then there's power involved and you are doing work. And that brings us to Lenz's law. Now, Lenz's law, an induced EMF will always oppose or tend to oppose the flux change causing it. Work must be done to cut flux. If you want to cut some flux with a generator, with a coil, you have to do work. And to make sure that you do work, the EMF will make you do work by opposing you, by working against you. An analogy of this is like friction. Friction always opposes motion. So if you are pulling something to make it move, then friction is trying to slow it down, and that's making you do work. So that is analogous to this, what we call a back EMF. Yes, so the EMF, the induced EMF, will work against you because it will make you do work, because that's where the energy comes from. Yes, and that's why we have the negative sign in this equation. Yeah, the induced EMF equals minus delta n phi over delta t. And that tells us that the back EMF, the induced EMF, is working against us. It's trying to stop the flux from being cut. Usually the negative sign is just cosmetic. The kind of questions that you'll get on this will be showing that you understand what's going on. So hopefully you've seen this. You drop a magnet in a plastic tube and it falls really quickly. You drop the same magnet in a copper tube and it falls slower, much slower. Okay. Use the laws of electromagnetic induction to explain why. 5 or 6 marks. Okay. Do you want to have a go yourself? Make some notes. I'll show you my answer. Okay, from Faraday's law. When the magnet falls through the copper tube, an EMF is induced as the copper cuts the flux produced by the magnet. The EMF will produce circular currents in the copper tube, and these currents will produce a magnetic field of their own. From Lenz's law, the induced field will oppose the motion of the magnet, i.e. the change in flux producing it. With a plastic tube, it's not a conductor, so we don't get an EMF. Notice the laws of electromagnetic induction, Faraday's law, and say what it is, Lenz's law, and say what it is. Okay, and then with those two, we can explain why it takes ages for the magnet to fall through the copper tube. Here's another one. Can you do this one? Hopefully you've done this experiment as well. So we're dropping a magnet through a coil, and the coil is attached to an oscilloscope, which is basically telling me the voltage or the EMF against time. A magnet is dropped through a small coil which is attached to an oscilloscope. Use the laws of electromagnetic induction to explain why the voltage at Y is bigger than at X, and why the two voltages X and Y are at opposite signs. One's positive and the other one's negative. Again, if you want to have a go at that yourself, make some notes. My answer is... So from Faraday's law, we get an induced EMF because we're cutting flux, and the EMF is proportional to the rate of change of flux. And that's why we get a bigger EMF at Y, because the magnet is traveling faster. Because when we let go of it, it accelerates due to gravity. So it's moving faster at Y. So we get a bigger EMF. The rate of change of flux is bigger, and therefore the induced EMF will be bigger. From Lenz's law, the induced EMF will oppose the flux change causing it. So when the magnet is falling into the coil, the EMF will produce a field to try and stop it coming in. When the magnet is falling out of the coil, the induced EMF will produce a field to try and stop it falling out. Okay, so at X the magnet is falling in, at Y the magnet is falling out. So from Lenz's law, the induced EMFs will be in opposite directions because it's trying to stop it from happening.